Today we start second chapter of aerodynamics. Please let me know if you can hear my voice. Talis?
Yes, hear you.
Sorry.
Okay, thank you for confirmation. You have a hand raised. So if you have some questions, please write in the chat. And today we talk about fundamental principles and equations. Equations which we will use in further discussions of aerodynamics and next course in gas dynamics. Many of definitions which you will see today you already studied not once but several times. So I hope it will be not so much difficult for you to see again these equations. If you will have some questions, please let me know in the chat or by voice, and I will try to answer. Okay, fundamental principles and equations are very similar to fluid mechanics. You already studied previously. It's a discussion about principal parameters that describe flow, equations that describe flow. And this chapter is consisting all the aerodynamic tools we need to have. We talk about some vector relations, or let's say differently, Anderson explains about vector relations and flow equations like continuity, momentum, and energy, three main flow equations. And then very useful concepts for implementation of the basic flow equations. They are substantial derivate, streamline function, equation of streamlines, vorticity definition, circulation, stream function, velocity potential, and some solution of practical aerodynamic problems, introduction. Chapter 2 is mostly about equations, so it's I will try to give you in a way that would be more closer to practical applications. Vector relations. I will discuss very briefly many of these concepts because I think you already know this from previous courses, as I told. We have question of Gabriel talking about deeper into the operation of flaps in aerodynamics. Of course, we will talk about flaps and not just flaps, other aerodynamic structures that allow to improve aerodynamic characteristic and control airfoil. It will be a section of airfoils very soon, and we will talk about it. If you are interested later, I will give you pages in the book that, of course, we will study later. I think it's extremely important, and we'll pay a lot of attention on design of flaps and characteristics. Going back to our discussion, we see vectors and different operations with vectors, addition, subtraction, scalar product, vector product, something that we already know. We see typical coordinate systems, Cartesian coordinate system, cylindrical coordinate system. Also will be spherical coordinate system, relation between them. These are three-dimensional coordinate systems that require three parameters to describe. For example, in Cartesian coordinates, it's x, y, and z axis. In cylindrical coordinates, it's a radius, angle, radius r, angle theta, and the z coordinate. In case of spherical coordinates, we describe position of any object using r, distance from origin of coordinates, and two angles, theta and phi. Fields of parameters is quite important to understand that any flow parameter, like for example, thermodynamic parameter, they are usually function of space coordinate and time coordinate. We may find such general definition of any thermodynamic property, as you may see here, that any parameter will depend on this space position and time. You can see it's 4 independent parameters, right? So if we would like to describe field of flow, we need to describe not just values, right, but also functions with respect to these 4 independent parameters. It concerns not just Cartesian coordinates, but also cylindrical coordinate and spherical coordinate system. In all these coordinate system, we see that something there is in common, right? Always first coordinate is linear coordinate x, here in cylindrical r, in spherical also r, distance, right? Then 2 other coordinates, they are or linear coordinates, distance, or they can be angle and distance, or they can be 2 angles. And the last coordinate is always time coordinate for all of types or all types of coordinate systems. When we are talking about velocity, we see usually it as a vector. This vector of velocity can be split in 3 components, x, y, and z component, for example, for Cartesian coordinate. And each of these components, scalar function, can be seen as a function of 4 parameters, 3 space coordinates and 1 time coordinate. In such a way, we can describe our vector function. We usually just have not so many vectors, right? We have vector of velocity, and that's it. All other parameters or vectors of parameters we can describe defining this velocity direction. Inside the other coordinate system, we can describe in the same way. Also, we can see scalar and vector products, things that you know from mathematics. Scalar and vector products in different coordinate system. Thing that I will pass really fast. If you are interested in this, or you would like, let's say, to repeat these definitions, always in Anderson you can find this information. The book is available for you. You know, we have a lot of books, and also I think there is online access, so you can read this book. Gradient of scalar field is defined as a gradient function, right? In this way, as known, gradient is related to constant or isolines of property. For example, any scalar property can be shown as a constant level lines. In such representation, we will study in further discussion of aerodynamics. And these isolines, they are very nice way to show distribution of scalar parameters in computational domain. For example, to show distribution of pressure around airfoil, we use definition of isolines, or let's say differently, that Fluent uses definition of isolines and plots these isolines and fills them with different colors. In such a way, we can see in which limits we have each value of pressure. When we would like to see gradient of this parameter, like pressure gradient, for example, we know that it's always perpendicular to constant lines. For example, if I would like to see pressure gradient in some arbitrary point, I need to make a perpendicular line to isoline, and I can see where gradient of pressure goes, for example, in each particular point, always perpendicular. I hope my lines are perpendicular, so let's assume they are. Isolines have direction always perpendicular to gradient lines. Unfortunately, I think Fluent does not show gradient lines, but we always can do such visualization when we process results of simulation. Okay, gradient fields or gradient of a scalar field is quite known definition. Divergence of a vector field is operation that tells about rate of change of volume per time, as we will see future, can be calculated in a such way. For example, in Cartesian coordinates is this diversion of a vector field giving to us scalar quantity. In Cartesian coordinates is a sum of respective velocity components by corresponding directions. dvx, it means velocity in x direction by dx by x direction, and sum of these quantities gives us divergence, so-called parameter divergence. Divergence can be calculated over a vector. Okay. Only over a vector. It can be seen such a formula not just for Cartesian coordinate, but also for cylindrical coordinate and for spherical coordinate. I think in some future applications, we will see the cylindrical coordinate divergence, and we will see how to use it in some practical examples. Curl of a vector field is giving to us information about rotation of flow. Flow rotation or angular velocity can be calculated by curl of a vector field, and its determinant of matrix, which you can see on the screen when you open this determinant. For example, for Cartesian coordinate, you can find formula for this curl or angular velocity. Angular velocity will be very important very soon. We will see how it's used depending on the value of angular velocity. We will see two different types of flow. In case of angular velocity equal to 0, we will say that such flows are irrotational. And in case of angular velocity not equal to 0, it will be rotational. Why it's so important? Because irrotational and rotational flows have different flow models, different simplifications and different flow models. Irrotational flows are usually much more simpler in terms of analytical calculation. Such a curl of a vector field can be calculated also for cylindrical and spherical coordinate systems in a similar way that you can see for Cartesian coordinate. Just open this determinant of this simple matrix 3 by 3, and you can obtain rotation in cylindrical and spherical coordinates. Curl of a vector field is also a vector, as you can see from these formulas. It has 3 components, right, corresponding 3 directions. Okay, 3 directions. Line integral, I think it's known what is line integral when you are integrating some function over the line. I hope you do not need to have explanation what is integral. There is also volume integral when we are integrating inside some area. right? Can be integrated as scalar value like P, or let's say it's a pressure. So when we're integrating pressure over some surface, we receive force, right? We can also integrate some vector, okay, and receive a scalar as a result, and of a vector over open surface surface integral, and the result is also a vector vector product. Volume integrals, as you also know, they are important in aerodynamics. For example, first one is the volume of scalar rho that gives us mass. When we are integrating density over the volume, we receive mass, right? And also can give a vector when we are integrating vector quantity over the volume. Relation between line, surface, and volume integrals, they are also important in transformation between aerodynamic quantities. First one is here transformation of line integral to surface integral. It's so-called Stokes theorem. Right. The second one here is transformation from surface integral to volume integral is divergence theorem. Right. And the third equation here is transformation from surface integral of scalar value to third integral of scalar value is so-called gradient theorem. These transformations would be important when we find simplified equations in aerodynamics. I think very soon we will use these formulas. Again, I would like to remind you about definition of control volumes and fluid elements. Probably you already know what are control volumes and fluid elements, so we will go back to that slide, which I found a bit later. We have two big definitions. Finite control volume, for example. What is control volume? Control volume is some big space inside which we have flow happening. For example, it can be a complete volume of study. For example, volume around airfoil, huge volume around airfoil, which you can see in a simulation, we are calling control volume. There are some properties of this control volume that should be satisfied, for example, conservation of mass, conservation of momentum and energy. And there are two types of control volumes. Control volume, which you can see on the left of this picture, is fixed in space volume through which we have flow of medium, of gas, for example. And the second one on the right is control volume, which is moving together with the fluid. Okay. First one is called Lagrangian approach, Eulerian approach, and second one is Lagrangian approach when the volume is moving. The result of calculation for Eulerian and Lagrangian approach in general is same. It's just a question, where is the observer? It stays outside of the control volume and calculates quantities of mass or that enter and exit this control volume, or observer is inside the control volume and is calculating the formation of this control volume and its movement in the space. In general, if we create correct equation system, both of these approaches give us same result. In some cases, more convenient to use fixed control volume. In other applications, more convenient to use moving control volume. It's a question of simplicity of a model, and maybe a question of physical process that we are looking for. For example, if we are looking for flow of air around airfoil, probably it would be more easy to use fixed control volume around airfoil, like we do when we simulate flow around airfoil. And if, for example, we are looking for the formation of fluid that of bubble fluid that goes in flows in some duct, probably would be easier to see this process of movement of fluid. So control volume in general, it describes large size object. In opposite, we have fluid element approach, infinitesimal fluid element approach, which works with infinitely small volume. Right? Infinitely small volume can be fixed in space, like you see on the left of this picture, can be moving in space, as you can see on the right of this picture. When it's fixed in space, it has constant volume and it has to account balance of mass, energy, and momentum through its surface. And when it's moving, it has a constant mass inside already. Its shape is changing according to interaction with other fluid elements or other small elements which surround this element. When we have a fluid element approach, we work with a big number of fluid elements interacting with each other. When we work with the control volume, we just see this one big volume. Right? Once we start to divide this control volume in pieces, we go from control volume to finite element approach. Okay, finite elements, all the big number of finite elements, all finite elements form for us a control volume. Both of these approaches, they use very similar ideas to take into account processes which take place inside them, like mass conservation, momentum conservation, and energy conservation. Which one is better? We cannot say definitively. For each particular task, we have to choose type of fluid, let's say, control volume approach or finite element approach. And we need to choose also fixed or moving fluid element. When we choose finite control volume, we can calculate only balance inside this big volume. For example, we can see balance of mass, energy, and momentum. General big balance, like say, like one number per all the control volume. For example, this is useful when we are calculating reaction force of all airfoil. If we do not need a particular distribution of pressure, for example, and we need just to know the reaction like lift or drag, we use control volume approach. But if we would like to see distribution of properties in each point, we would like to know how they are different. For example, these velocities over the airfoil, how pressure is distributed. We need to use fluid element approach, which allows us to see not just balance, but inside particular point, which are the flow properties. All CFD methods are based on a fluid element approach. There are also others, but okay, it's the most common. But almost all analytical methods for calculation of aerodynamic quantities are based on control volume approach. When we see a global balance, we can calculate analytically. When we would like to see point by point, we using CFD methods and fluid element approach. Flow field can be specified by parameters which you can see on the screen. To describe simplest case of a three-dimensional fluid field, flow field, we need to describe thermodynamic properties of this flow field in all directions we have. And we need to describe also velocity functions in all three directions we have. In case of three dimensions like this. In case of two-dimensional, of course, we will have one simplification, right? And this will also not exist. In case of two-dimensional calculation, instead of 4 independent parameters, we need to have 3, 2 coordinates and time. There is also another simplification that we might adopt. Is very useful when we see stationary flow, when there is no time. I will cancel from here time, and we see stationary flow which does not change in time. It requires only 2, in case of two-dimensional flow, only 2 dimensional parameters, and simplifies significantly flow model. Almost all analytical models which you can find in book of Anderson are solution in case of stationary flow in two-dimensional case. Okay, so as when possible, we will try to go from transient with time to stationary without time, and from three-dimensional with Z coordinate to two-dimensional without Z coordinate. In such case, also I forgot to cancel W component of the velocity in two-dimensional case. Okay, this definition, I hope they are clear. They are not so complicated. Let's talk a bit about continuity equation. I think you've heard already a lot about it. Just a few more comments. What is continuity equation? It describes for us conservation of mass. It says that quantity of mass which enters inside our system is the same quantity of mass which exits from our system, or mass can neither be created nor destroyed. So mass can just enter and exit without its change. There is a model. Probably you already saw this many times, such kind of model of mass conservation. This model results in this integral equation you can see on the bottom of the screen. Here in this integral equation, we have change of mass inside our control volume in time. And this change of mass inside volume and time is same as flow of mass through the surface. So change of mass is equal to equal to flow of this mass through the surface of our control volume. Of course, with negative sign, because everything that is in positive with time would be also going inside, and everything that goes inside has negative sign according to sign convention. Balance sum of these two quantities is equal to 0. So mass not created or destroyed in our case. Another comment about these equations, which you can see on the bottom, there are 2 types of equations we are usually looking in aerodynamics. Equation written in integral form with integrals. This equation is usually applied to control volumes. Okay. And on the right side, we can see same equation in its differential form. It's not same, but it's a consequence. You can find in the Anderson book how it's obtained. It's a very simple process. You just analyze quantities which are inside the integral, and you make transformation from surface integral to volume integral according to divergence theorem. Anderson shows how to do this, and I would not like to stop on this question. This one is for finite element. Since this equation is written as differential form, it can be applied to infinitely small elements. Also saying absolutely same thing that integral equation. First part is density change in time. Density is something that is relative mass per volume, right? Since volume is going to zero, we have just density. And this change of density in time is same as we have of change of relative mass in through the surface of infinitely small size. Okay. As I told you, there are two types of flow: transient flow and stationary flow, or steady flow. I think it's the same definition, stationary and steady. Transient flow is working with the processes with change in time. So we have integral form of continuity equation that deals with the time, has time derivative on the left and on the right. And when there is no change in time, for example, we have flow which doesn't change, you have constant velocity. Let's assume the following picture, airfoil and constant velocity. After some time, this flow establishes in some way which does not change anymore. At any second is absolutely same distribution of velocity, distribution of thermodynamic properties. It will not change in time. So all time derivative, not just from continuity equation, but from other equations also, they are equal to zero. When flow is stabilized, these parts of equations are equal to zero, and it means that we can use stationary form of flow equations. Stationary equations are much simpler than transient, and usually they might have analytical solution for some particular cases, at least. Okay, with the transient flow, any analytical solution is not possible because it uses partial time derivative, and it cannot be solved analytically. In integral form, stationary equation, and in differential form, equation 54. Second equation is the momentum equation. Principle of momentum equation, I hope you also remember, is the force that equals time rate of change of momentum. So on the left side, we need to combine all forces in our system, and on the right side, we need to take derivative by time of momentum. Our forces are having two different sources. They can be body forces and surface forces. Body forces, they are some forces acting on the complete body, on the complete volume. They are, for example, electromagnetic forces or gravity forces. And the surface forces which act on the surface, they do not act inside the volume, they act only on the area of surface. And this pressure force is representing to us the surface forces, the surface force. Okay, so total force vector, as you may see on equation 59, can be composed of three different quantities. First is body force, then pressure force, and the third one is viscous force. Here we do not talk yet about viscous force. In all aerodynamics, it's not defined, so we will consider it or equal to 0, or we will say that it's some force which we will talk only at the end of the book, in the end of our theory. And you know the reason of this. Usually it's because viscous forces cannot be solved analytically and can be solved experimentally, numerically. And this does not bring to us any advantage in analytical solution of aerodynamics. It only brings more complexity, but they are necessary. They are necessary. For example, you remember for streamlined body flow of airfoil, the drag is composed by viscous forces. So we need to know viscous forces to calculate drag. And this is done later. Okay, in terms of change of momentum, on the right side of equation of momentum, we have two sources also, that it is net flow of momentum out of control volume across surface, and time rate of change of momentum due to unsteady fluctuations. These unsteady fluctuations, they are basically change of momentum due to all other sources that we already mentioned before. Okay, so G and H. This flow of momentum through the surface is the first part here. You can basically see momentum calculated and integrated over the surface. And unsteady fluctuations in time is this one, is a balance of momentum and how it changes in time. Now we combine left and right side of equation, combining forces and the rate of change of momentum in time. We obtain this equation 264 in its general form, in integral form. Of course, this equation always can be simplified. We will see very soon how it can be simplified for stationary flow. And this vector equation in integral form can be also written in its differential form to be used in a fluid element approach. So equation becomes split in three different equations with according to the coordinate system chosen. This one here you can see for, I think it can be used for any. Oh, it's just for Cartesian coordinates. Cartesian coordinate system. Okay, it has some similarity. All these three equations are similar. It's just changing component of the velocity here in this fluctuation part, right? This component of the velocity is changing on the part of, let me see, flow of momentum through the surface. We also choose different component of the velocity for each coordinate direction. And pressure force is calculated by taking derivative of pressure on its corresponding direction. So then body forces and viscous forces we generally do not specify, and we will not use in the near future this part of equation. So we can, after this discussion about equation system, we could neglect until the end of the book when we start talking about viscous part. simplifying momentum equations, we make viscous forces, yeah, and body forces equal to 0, and also transient part of momentum equation can be also neglected. This part here we will not use in stationary form. So our momentum equation reduces to such simple form in its integral version equation to 71 and its differential form equation 72. For us, it says that there is a balance between surface integral of momentum through the surface and pressure forces. So that's simple balance. And in its integral form, in its differential form, it's very similar to the previous one. We just use divergence theorem to make such transition from one equation to another. Application of momentum equation is very interesting and very important, I think, to understand. It's one of the reasons why we are studying equations, because they simplify models, and just with the few of equations we can find a lot of information about flow properties. Here, this picture application of momentum equation corresponds to some example in the Anderson book. Is section 2.6 application of momentum equation. If something would not be clear, you can see in the Anderson book. Which is the problem we might see here? We have, for example, some airfoil with known geometry, and we would like to use our flow equations, in particular momentum equation, to obtain drag over this body. What we can do, we can measure this drag. Not always, right? Sometimes we can measure this drag, but the momentum equation has such a nice property that applying this equation to experiment, you do not need to put any additional, let's say, tool or sensor to measure distribution, or not to measure the value of this drag of airfoil. As I told you already, it's extremely difficult to measure drag of airfoil because usually it's small, right? Drag coefficient is very small, so drag force is also very small. Maybe our sensor will not be so sensitive. And if we could use power of equation and obtain it in a more reliable way, it could be much more interesting than just to measure directly. So it was a problem that was solved a long time ago, a very long time ago. And I think it's useful to know how momentum equation could be used to measure or to calculate drag. Okay, we measure partially and we calculate as well. Here you can see airfoil, two-dimensional body inside the wind tunnel. And we have uniform velocity entering on the test section. And not uniform velocity is exiting from test section. It has some distribution. U1 is uniform velocity which enters, and U2 is some function, some distribution of velocity which exits from the test section. Okay, this non-uniform velocity can be seen in visualization, which you might see on figure 20 on the right side. here it's visualized by small bubbles, because all this flow is not inside air, it's inside water, right? And if we put a very thin wire in this water and make some current, we can see dissociation of water, and some hydrogen bubbles will appear. We make these, I'll say, pulses, several pulses, and we can see bubbles moving together with the flow, and they represent velocity of the flow. These bubbles have a so small size, so they almost not disturb the flow, and they are moving with absolutely the same speed as flow moves. Here on figure B, you also can see that it's not just one wire. There are two wires. One is here, and the second wire is here after some distance. So they pull together, and to see velocity propagation over some distance. I think it's important because anyhow, these small bubbles, they start to disappear. They start to mix with fuel. Flow structure is not kept as perfect as it theoretically needed for analysis, and it's nice to do visualization by two wires in a distance than just by one wire. So we can see longer propagation of velocities or, let's say, trajectories of flow. We can see that we have just one velocity component on schematic A, just one velocity component, which is u component of velocity, right, in any arbitrary direction. And the same we can see here, right? We can see that flow does not rotate in any point here, so it continues to be translational. Okay. That's I think it's interesting. It's an interesting thing. To apply momentum equation in such example, we will choose a shape shown on figure A. This shape is described by a complex. Okay, it's not simple. It's shape A, starting from A, B, C. AB is streamline far away from body, so it almost not disturbed. Velocity and pressure stays constant along this line, so it's not near body, it's quite far from body. Body does not interact. And then we have line BC. Over this line, we have change of velocity, because since body interacts with the flow, it creates some disturbance inside velocity. Since drag force or reaction force is generated, we have decrease of velocity U2 at some region, at some zone. Then from point C to D, we have a horizontal line from end of the maximum coordinate of control volume to the trailing edge of our airfoil. Then point DEF, line DEF is describing shape of airfoil. Is on the airfoil, inside the flow. It's not something. It's not a line on the body. It's okay. It occupies same geometry as body geometry, but we consider this still inside flow. Okay, it repeats geometry of airfoil. Then FG has absolutely same size and direction as CD, is practically repeating this this line, so CD going in this direction, FG is same line but going in opposite direction. And physically, these lines CD and FG are on same coordinate. So when we will see transition from one zone to another, we will not see anything because it's okay. It has zero thickness. Okay, all the flow is joined through lines CD and FG. And after G, we have H, where we have a transition of flow due to interaction with the body. Okay, so there is some profile of velocity for symmetric airfoil. As you may see on picture B, this airfoil looks symmetric. Profile of velocity on lower side will be same as profile of velocity on the upper side. For non-symmetric airfoils, they will be different. They will be different definitely, but of course we can see this profile. And line HI also is described by streamline, and it's far from the body, so it has pressure equal to infinite pressure, as well as velocity equal to infinite velocity. Okay, and then the final line AI is inlet, where velocity is uniform. This line AI is also far from the body, or in front of the body, and it is not doesn't have influence from the body, not influenced by the body. So velocity is uniform there. One comment about this line on the top and on the bottom, I will show it by other color. This AB and HI, of course, they will be excluded from our calculation because these two lines are described by streamline. So flow is always tangential to this surface. So there is no quantity which could enter or exit this control volume through this upper or lower surface. So there is no flow in these directions. For us, it means that we will not calculate flow of momentum through these bonds because velocity is tangential, so physically cannot cross. And also, as I already told you, it will be no flow here of momentum, right? Because it's bounded with the physical body. It located on the body or very close to the body. So there is no flow here. And these flows over HCD and FG, we also disconsider because is same element. For example, let's assume that some quantity goes from lower side to upper side. So, but it means that it still stays on the lower side because it's connected physically, right? It's connected physically. So this flow mathematically does not exist for us. So what will happen? What will exist? Which kind of balance of momentum we need to take into account in such case? First of all, it will be balance. It will be momentum on the entrance. Okay, momentum on the entrance, which enters inside control volume. Momentum which exit through control volume, this BC and GH here. And part of force, because if you remember, just told a few minutes ago that momentum equation deals with balance of forces and the rate of change of momentum. So, and for only force we have here appears on the wall. All other forces are equal to 0. because they are far from the body, pressure equal to infinite pressure, so there is no pressure difference far from the body, and all other forces except this force that acts on the body, pressure force which acts on the body, all others are equal to 0. So these red lines which I showed you here are only quantities which we need to take into account to calculate force balance for momentum equation. Okay, there is some discussion about this, which I just explained to you, that there is a reaction force. We would like to look in general is, okay, it's directed in according to flow. Okay, it's not obligatory horizontal or vertical. It has arbitrary direction, but since our flow goes in just in one direction, we say that reaction force and drag force is the same force. We do not see any lift force here, at least for experiment which Anderson shows. For symmetric airfoil, lift force does not exist. So we have, instead of reaction force, we have drag force, and we have balance between this drag force and momentum which we have on entrance and exit from this control volume. Okay, this balance of forces we might find on equation, this one here, and it's also shown that part of forces on pressure on a far distance from airfoil, they are equal to 0. So we are not considering this pressure balance far from airfoil, and we consider just flow inside this equation of drag. We consider just flow of momentum through inlet and outlet. Integral can be open. Okay, integral is split in two integrals. Okay, let me see here. This integral here is split in two parts. Initial part, AI, which is integral from I to A of density 1, velocity 1, dy, and the final part, which is right here, is integral from H to B of density to velocity to dy. Pay attention that in Anderson book, as you may see here on the right part of this slide, there is an error. You may find it in the book that he writes this formula, is right here. It's not correct because it contains, but it's just misprint. It's not error in theory, nothing like that, just misprint. Instead of density, they wrote pressure, but should be density. Already in the 6th edition, this error was fixed, and this formula is correct. Okay, so pay attention when you study a book that in the 5th edition there is some misprint in formula of drag in this example. So integral of force, of force is written, and we can simplify it when we will consider. Okay, let me see if it's here. Yeah, it's here. When we will consider that density is constant, because we have incompressible flow, so density is same everywhere. Density 1 ρ1 is equal to ρ2, and just we use ρ in our definition, and previous formula of integral can be simplified to this one here. To this one here. Okay, just a moment. Okay, Let's see with attention this integral. I hope you understand why this formula here is equivalent to this formula here, because we just substitute, right? We use this, let's say, these limits. They are same limits as BH, as you may see from discussion from Anderson book. So we can use same limits, not AI limit, but we can use HB limit. And this is why we can do it. When we look on this formula, when we are seeing that we are integrating some quantity, let's see. Okay, I would like to analyze this formula here. Density is constant. Okay, it has always some value. What happens with velocities? U1 is also constant. Okay, U2 is changing. This is changing and this is changing. But how is changing? It's not an arbitrary value. When we see experiment with this wire, we can see that far distance from axis. Okay, I will put axis here. This is the axis. This is, let's say, distance y direction. Close to axis, velocity is changing, right? We see profile of velocity. Far from axis, starting from somewhere here, or even closer, somewhere here, velocity is not changing anymore. In all this range, I will probably use other color. In all this range here, velocity stays constant. Same thing we can observe on the upper side here. Velocity stays constant. Sorry, my line is not vertical, but supposed to be. I will try one more time. If it more or less, not so vertical. But okay, this is constant velocity. But how much is this velocity? Already we consider that this velocity is far from airfoil, and we will see that this U2 is equal to U1. It's same velocity as we had uniform velocity before our airfoil. If we know that velocity U2 would be same as velocity U1 in some range, okay, starting from some point y limit, right? And until infinity, it will be continue same velocity. It means that in all this yellow line, this difference would be equal to 0. So this difference will be not 0 only inside this limit here. In this range, we will have some positive difference of velocity in this blue range. Outside of blue range, we have always integral equal to 0. So it's not important how long we are calculating, if our control volume is okay, like in this size, or our control volume is bigger size. Everywhere where we are meeting our yellow line, integral will be equal to 0. So it's it limits calculation. We need to calculate only region where our velocity is changing. And at this point, integral will not be equal to 0. At these points, integral will not be equal to 0. And this, as you may see, some thickness, which could be compared with thickness of airfoil. Approximately, okay, looking to this picture is more or less 3 times, maybe 4 times thickness of airfoil. So we can use this limit, we can define this limit as plus minus 2 thickness of our airfoil. This is where we need to calculate the integral. We do not need to calculate it in a very far distance, right? Okay, so drag will be function of velocity change. Velocities are possible to calculate using such rake of pitot tubes. And this is an equipment which takes distribution of velocity in several coordinates. Okay, so this rake can be installed in front of, after airfoil, and can take distribution. Each of these tubes gives a value of velocity at its specific point. So we have airfoil like this, then we install this rake. It reads distribution of velocities, and then analyzing this distribution of velocities, we can see this curve of velocity profile. Okay. This is how experimentally is done such measurement. This equipment is not complex. I think it's even simple, right? It requires some big number of tubes, but these tubes are very similar and not so expensive. The only condition, I think, for this rake, it must be very light and thin, not to disturb much flow structure. So flow structure should not suffer disturbance due to existence of this tool. Okay, I would like to remind you that you can ask your questions if you have some. Another comment on all this application of momentum equation. As you saw, we used momentum equation to calculate drag over airfoil. So we do not connect any kind of sensor directly on this airfoil, and we are capable to calculate this drag force using our theory and using some device which measures distribution of velocity in a distance. So this is indirect measurement of the drag force. As a consequence, we can say the following: we do not need just to have airfoil to measure this drag. We can use a model of more complex or more simple, let's say, cylinder. We can use this formula to calculate drag on cylinder. We can use a small model of airplane, small scale model of airplane, and we can introduce inside the wind tunnel and see distribution of velocities, and analyzing distribution of velocities far behind this airplane, we can have conclusion about values of drag force over this airplane. We are not limited by complexity of geometry, I think. We can measure something indirectly. It gives a lot of opportunities in experimental aerodynamics. In some cases, it's very difficult to install sensor directly on the body, so our body will have no sensors, will have pure flow around it. And analyzing flow behind the body, analyzing this flow disturbances behind the body, we can see which is drag created by this body. And we can, making some dimensional analysis after, as we saw by Buckingham-P theorem, for example, we can conclude what will be drag on a big or full-scale body. This is one application of many of momentum equation on aerodynamic body. This function does not have any restrictions to be used in more complex bodies or more simpler bodies. It can be used for any aerodynamic structure. Our other example, I think we will see soon. Yeah, here is probably the last example for today is application of momentum equation to estimate profile of boundary layer. We are interested in this case, and we can use same approach as we had in the previous example. We will construct control volume. This control volume you can see on figure 23. This control volume has one edge, front edge, which is perpendicular to flow, and it has undisturbed flow V infinite, velocity infinite. It has edge far from wall. It corresponds to streamline, so flow will not cross this streamline. Okay, I will probably delete this. It's not looking nice. And the backside of our control volume is this one is the velocity profile which we are looking for, and lower side of our control volume corresponds to the body. At this point, we know that velocity is equal to 0 on the wall of the body. So our control volume is closed, and we can apply definition of momentum equation, or sorry, equation of momentum to this model, and we can calculate profile of velocity. To make possible calculation of velocity profile, of course, we must provide some experimental data. We have empirical relation between thickness of boundary layer and Reynolds number. Here on first formula, you can see it, that ratio between thickness of boundary layer and distance is 5 divided by square root of Reynolds number. Reynolds number calculated by C coordinate or C distance. I probably, it's written here, this Reynolds number formula, right? It has C inside. So it changed from 0 to its maximum value. Another experimental data which we provide is friction coefficient measured experimentally, CF formula. We know that friction coefficient is related to drag, dynamic pressure, and size. Right? From one side, from definition of aerodynamic coefficients, and from the other side, it was measured experimentally as function of Reynolds number. It's 1.328 divided by square root of Reynolds number. And we are looking for velocity profile. Here, we would like to find which is velocity profile written in such form that it will be proportional to V infinite. It would be also proportional to ratio of y coordinate divided by thickness of boundary layer in some power of n. The only parameter unknown here is n. So this is what we need to find. To make possible such solution, we use result from previous example. We already saw that for such applications could be used definition of drag according to this formula obtained previously. Is same idea that flow is incompressible, so density is outside of integral. And inside integral, we have velocity after the at the exit of our control volume multiplied by difference of velocity between entrance and exit. So this integral will always be positive because u1 minus u2 is always positive value. Okay, and then we integrate from h to b. In our case, h is this lower side of control volume, and b is upper side of control volume. You know, theoretically, profile of boundary layer or velocity profile is infinite, right? So at the infinite distance, we will still have some small change velocity, and this would be, as we may see from the book, this can be simply solved when we are going to limit of function. Okay, how to solve all this? We know that drag is, sorry, I will make some new lines here. This drag can be taken from equation. Okay. Then this Reynolds number definition can be taken from its definition here, right? And the thickness of boundary layer, or this, goes here in this formula. When we combine together all these four formulas, as Anderson shows, we obtain equation that can be solved analytically. And the only unknown here in this equation system, right? Can write it in, for example, any mathematical software, or just follow Anderson book. I will not do it. I think it's very simple, but consumes a lot of time for transformation. We can find that solution of this equation is having two roots as a final. Just a moment, I will find here why it has two roots, because we, analyzing this equation, we have somewhere, yeah, because of this square root, no, because of n in the denominator, right, n in power, we start to have square equation. Just a moment. It's here. Square equation. The following one. It says to us that 1 divided by n plus 1 minus 1 divided by 2n plus 1 is this empirical coefficient divided by 10. Yeah, we know that this empirical coefficient is was introduced in definition of friction coefficient. If you are interested to follow how this equation was obtained by combining previous equation, you can do it. I think it's just a mathematical transformation. So anyone, even without knowing aerodynamics, could join these equations in a system. Solving this equation, it's transformed to just a square equation of parabola, second order. You can find two roots. Root 1 is n equal 2, and root 2 is n equal 0.25. Both of these solution can lead to the same consequence. Just a moment. But only one of these solutions has some real meaning. We can see it if we compare these solutions with actual laminar boundary layer profile. You can see that N0.25 fits much better than N equal 2, so it's not solving for us, and not just because it fits better, because we need to see how velocity continues to be after boundary layer. It goes in this direction here. So if we, for example, would adopt n equal 2 as solution, we would see break in velocity, in velocity derivative, and this is absolutely not happening in real flow. Real flow is smooth. It has smooth transition from boundary layer to outside. It means that only this curve can provide N0.25 can provide such a smooth transition from boundary layer to outside free flow. We can see that actual laminar boundary layer profile is not same as our analytical solution. So let me go a bit back. I will write you a complete formula. It's this function. Okay, it's not written here. This function is u is v infinite, as from previous slide. I just writing from previous slide, y divided by delta powered by 0.25. My infinite is not so beautiful. Maybe I can make it better like this. We see that this function does not fit well with the experiment, right? And you may ask, okay, what is this? Since we use analytical solution, we have an exact solution of flow equations. Why profile of experimentally measured actual laminar boundary layer does not match with our model? Because we have difference in all points, right? We see that there is a difference everywhere in velocity profile, except 2 points. We do not have difference at starting point, 0.0 velocity, and at final point, where our boundary layer finishes. We also do not have error. In all other points, we have error. This happens because of one reason, and this reason is called control volume approach. This is one of disadvantages of control volume approach. Because if you remember, I told you at the beginning of this lecture that control volume approach, it uses a global balance as and calculates global balance. So it does not see any particular behavior or any point values of velocity profile. It calculates just a balance. For model of boundary layer, global balance is to satisfy condition of 0 velocity at 0 point and infinite velocity at infinite point. So this is a balance. These are balance criteria for boundary layer theory. This is why we have no correspondence in the middle. But in the global, in general, we have solution. Okay, if we would like to have an exact solution that corresponds with actual laminar boundary layer velocity, we have to use finite element approach, and only numerical simulation could be used in, okay. No, let's change a bit. Numerical simulation is the best way to obtain this profile. But there are analytical methods and analytical solutions, not so analytical solutions. There is a solution which is a numerical solution of boundary layer theory. We will see this numerical solution at the end of gas dynamics. There you will see that it can correspond, let's say, very accurately to actual laminar boundary layer profile, but only when you are solving a set of ordinary differential equations. Oh, sorry, I'm already tired a bit. I'm speaking different words instead of words that I should say. Please let me know if you have some questions, and I can have a short break expecting your questions. Okay. This question of energy equation we will start discussing next lecture. Please let me know if you have questions about today's class. Before you send something, one more announcement that tomorrow we have class, our big class, where I will show you many things about doing work one, how better to present some aerodynamic quantities, how better to show results, which are typical errors, some suggestions. Is not something that I would like to see, just not because of me, right? Because in world of aerodynamic science, we have some rules, and we expect to obtain good quality results, right? So according to these criteria that I will try to explain you, I'm expecting that you will do your work. Just this as suggestions, highly suggested, because if you make something similar in future, you will be also expected to deliver in such quality. So this is why I think important to discuss more about way of presenting your results than just calculation. Calculation, just apply formulas and it's there, right? But it's very important to sell your results, to sell yourself, to obtain better job, to obtain better salary. And for this, you need to know how to present in a correct way, how to format in a correct way. And aerodynamics, if you see book, there are many beautiful pictures, many beautiful graphics. All graphics which we might see in Anderson book, they are super nice, right? Very simple to understand, explained, like format, looking nice. And this is something which I would like you to study and present in your reports. I think it's very useful for, in general, for engineering to be understood and well evaluated. I think tomorrow will be a unique opportunity for you to ask questions about work one, because soon you will need to present and send me this work. I think it's like 2 weeks from now. So prepare everything you would like to ask tomorrow, and we discuss as much as possible. And since there are no questions, have a nice evening, and see you tomorrow then with your questions. Thank you for participation today.